Okay, so good morning or good evening, everyone, and welcome back to the seminar series. So next week we've got Monica Oliveira coming up, and then I'll be sending around the lineup for February a bit later this week. So today we have Mazi Jalaal with us. There are lots of photos of Mazi on the web. This was from one of his many websites, and I think there he's celebrating his new position as assistant professor at the University of Amsterdam, where he's been since 2021, which is only pretty recent. He's got a beautiful website, by the way, that we were looking at last week, and strongly encourage you to have a look at that. And I'm guessing that's why he's looking very happy in this picture. So Mazi started with his bachelor's in the University of Tabriz. He did his master's and PhD at UBC, PhD with Neil Bamforth and Boris Stover. He then went to the Physics of Fluids group in Twente for a postdoc, and then another postdoc at Dampt, where he was last time we talked about, pretty much.
That's great.
He's won a number of scholarships and fellowships, a Vanier Scholar during his PhD, fellowships then in Cambridge. And he's also been very successful at winning awards and grants. I was kind of curious about how he won the Women's Engineering Society grant, but I'm not going to ask about that. And maybe that's why he's really laughing on the left-hand side here. Anyway, what's one of the nice things about Mazi, he's always smiling. He's always got something interesting to say. So Mazi, looking forward to your talk, and we'll pass it over to you.
Thanks so much, Ian. Much appreciate the introduction. I can say the West Women Engineering Society in the UK is a very nice organization, and they always welcome everyone to join, and they provide support for spreading basically science, technology, and engineering, and in particular attracting female students. So if you're in the UK, I highly encourage you to get involved with that. How's my screen? Do you see a full screen now?
Perfect.
Perfect. So first of all, thank you, Rob and Ian, for the invitation, and all of you for joining. This is such a great seminar series, and it's my great honor to be a part of this. So today I will tell you a little bit about yield stress fluids driven by surface tension, and in particular about our activities around droplet spreading and printing application. I really try to keep it relatively high level during the talk, and trying to entertain theoreticians and experimentalists by presenting both types of results. Hopefully it's as entertaining as the US politics, as Ian said, in the last 4 years, and what's happened today. So thanks again for being here. To make sure we are all on a same page, let me define what I mean by the term Plastocapillarity. So if you look into Cambridge Dictionary, here's a definition of plasticity. So the quality of being soft enough to be changed into a new shape. I really like this definition, always on a dictionary. So it somehow referring materials that manifest yield stress, because that's what you need to sustain a new shape. And if you look for the definition of capillarity, it basically says the force that causes liquid to rise in a tube or other narrow space. So the second definition is not that accurate. It obviously refers to surface tension, but we know it doesn't have to necessarily be inside the tube. So if you put these two together, you get basically what I mean by plastocapillarity. So when yield stress materials are deformed by surface tension forces. To see when plastocapillarity is actually important, we should look at the scale of the problem. So obviously free surface must be involved, but in what size, that's the question. So the easy way to do so is to look at the so-called capillary length scale. This is what I'm showing here with lambda c, which compares the surface tension coefficient, the root square of surface tension coefficient over the multiplication of density times gravity. So these are material properties. If you look at water, for instance, this is always order millimeter, right? So, but if you look at the literature on free surface viscoplastic or yield stress materials, most of them, the most majority, are looking at scales that are much larger. So here's an example. This is a mud slide in Southern California. And if you're looking at mud slides, lava flows, snow avalanches, we somehow manifest yield stress materials, the scale is typically several meters or kilometers, right? And if you're in that length of scale, obviously much larger than our capillary length of scale, so you don't care about surface tension, obviously. There's a big body of work on that area. Christopher Ansay have a review on JNNFM that reviews the work until at least 2007. It's a very nice read. But if you go to a smaller length scale, so here's an example. If you go to droplet size, then your characteristic length scale of the problem is close to your capillary length scale, right? So this is where capillarity is important. If your material is yield stress, then plastocapillarity becomes important. So I'm gonna, in the next few slides, I'm gonna somehow review the field in bringing some examples when plastocapillarity is significant. So the first are drops. So there are relatively few papers who've studied the drops of yield stress fluids. I got this picture from the work from the lab of Wolfgang Bertolo. So what is shown here is that the droplet basically dripping off a nozzle from left to right, the yield stress of the material is increasing. So we know for a Newtonian fluids, this has got this such problem shows through the Rayleigh plateau stability, the pinch off and droplet formation. But you can clearly see if you have a yield stress materials, as you increase it, the droplet becomes elongated. So the shape of this droplet is basically the result of competition of surface tension, who wants to make the droplet spherical, and the yield stress that resists such a deformation. Okay, so the group of Bertolo and some others more recently have looked at this problem. There are some other works from the lab of Cusseau, this beautiful paper of Luan Forte, and also the group of Randy Ewald, who studied droplet formation and impact. But most of them, especially the one I'm listed here on the right, they paid less attention to the surface tension because the regime they studied, surface tension is not actually that important. We also looked into the droplets of this shape recently. I'm just going to show you some videos. What we did was basically we let this droplet pass through an air-water interface, and through such a very simple system, what we showed that you can get a spherical, non-spherical soft particles, and also in some regime you can actually make capsules to encapsulate gas. I'm not going to talk about this work, but you can have a look at our paper. This was the work with a very talented undergraduate student, Dave Kemper, and in the group of physics of fluids of Detlef Lose. Right, so this is about drops. I come back to the drops later during the talk. But another part that viscoplasticity or plastocapillarity can be important are bubbles. The picture I'm showing on the left is from the paper of Dubesh and Frigard. What they're showing there is static shape of bubbles. If you put bubbles in Newtonian fluids, surface tension wants to make it spherical. But yield stress of viscoplastic fluid resists this, so you can get arbitrary shape like those shown here. There are some series of nice works from a group of John Simopoulos on the simulations of rising bubbles inside yield stress materials. John De Bruins also have done some work on that. More recently, the group of Valeria Garbin, now at TU Delft, also studied bubbles in yield stress material, in particular on the acoustic actuations. Really nice, beautiful works. our work on Plastocapillarity and bubbles was a slightly different than bubble in bulk of fluids. So we looked into bubbles like this, reaching the free surface and then burst at the surface. Again, I'm not going to go to the detail of this book either, but let me show a video. So basically, this fluid here, that bubble bursts at the surface, is now viscoplastic. In a work that actually came out today on arXiv, you can see how yield stress changed such a very dynamic process. In particular, you can see you get this final cavity shape, which is characteristics of viscoplastic materials and doesn't happen in Newtonian liquids. Okay, more related to the talk today is the process of coating. There are many methods of coating fluids on the surface, and in many industrial applications, these fluids are actually viscoplastic, or at least show some non-Newtonian behavior. One way of doing so is through inkjet printing, when you put single droplets on a surface one by one. For instance, a more common and known method is the dip coating method, when you have a piece of solid surface that you dip into your material and drag it out, and then you have this thin film deposited on a surface. The thickness of this film is actually also determined by surface tension, and if your material is viscoplastic, by the yield surface. So this basically is a very nice problem to study plastocapillarity. Again, the group of Crusoe actually looked into this problem, but the regime they studied, surface tension, if I remember correctly, was not very important. Okay, what really drove me in the past few years to study this topic of plastocapillarity is however the emerging industry of 3D printing. So here I have three examples of plastic, clays, and food 3D printers, and it's easy to maybe agree with me that none of these fluids are Newtonian, and I guarantee all of them have some yield stress, because that's what you need to make 3D structures. You need yield stress to keep the shape intact. And if you ever wonder how 3D printers of this type, there are many types of 3D printers, but the one that are so-called fused deposition 3D printers or extrusion 3D printers work, here it is. So basically, simply to make a 3D printer, all you need is a pressure source, a nozzle, a viscoplastic material, and a soft or hard substrate. So that's all you need for a 3D printer. What happens in reality in industrial sectors is that you put this pressure sensor on a robot, you program, you give the robot the CAD file, and the robot does the printing for you. So here is an example that I've done just last week. My material is carbopool, and the small nozzle diameter, and this is a speed up. So this is my nozzle printing something. I'm zooming in here. This is the first layer on top of the my plastic, this case actually deformable surface. After the first round is over, I start printing the second round, and you keep doing this. And if you have illustrious materials, you can print in 3 dimensions. Okay, so it's not a it's relatively an elegant science. So what happens is that you spread this material on the substrate, and then spread the second layer and the third layer on top of the liquid. So for that, basically, this motivated us to try to answer these 3 questions, which are the outline of my talk. That how does a viscoplastic droplet spread on a surface? Can we control this? Can we go a little bit smarter and control this spreading on a surface? And in the end of this talk, I will try to come to more modern 3D printing technology to avoid some difficulties. Okay, so here is what I call the simplified spreading problem. A problem is like this. I have a solid surface that is pre-coated with a thin film of thickness h infinity, and I put a droplet that is much larger than that on top of the surface, and I let it spread. Okay, so if the droplet is Newtonian, you can easily guess as time goes to infinity, this droplet spreads until it becomes fully flat. Nothing stops the droplet from spreading on the surface, right? I won't talk about Newtonian droplets because this is non-Newtonian fluid seminar series, but I just want to put a small note that even the Newtonian problem has a lot of interesting things to look into. With Carola Seifert and Jaakko Snoyer, we look at the same problem more recently. Very long story short, if you go to capillary numbers order 1, your smaller scale dynamics might go through some dramatic changes. So one should be careful about capillary numbers, even when talking about a simple Newtonian case. But our fluids, motivated by 3D printing industry mostly, are not Newtonian, they're viscoplastic. So what is a viscoplastic fluid? It basically has a yield stress. Below the yield stress, the material looks more like an elastic solid. And above the yield stress, it behaves more like a viscous fluids, but this viscosity is typically also non-linear, like shear thinning behavior. So you can draw or graphically show it like this. X-axis is my shear rate, y-axis is stress. If you have Newtonian fluids, it's a straight line passing through the origin. The slope of the line is your viscosity, but if you have a Bingham fluid or a viscoplastic fluid, you have this threshold stress. So you have this offset, that stress is the yield stress, and this, if the viscosity, the plastic viscosity is constant, you have a Bingham fluid, right? So you can, in tensorial form, you can write it like this: stress below the yield stress, no the deformation rate, tensor is 0, above it, you get deformation. Okay, so the problem comes now that if I replace my Newtonian fluid with viscoplastic fluids, I will get a final shape that is not flat, right? So my droplet spreads until the stress inside the droplet falls everywhere inside the droplet, falls below the yield stress, and that's the moment droplet stops moving, right? You can think about I don't know, cosmetic cream or your toothpaste that, you know, it doesn't spread fully. It did if it was Newtonian, didn't have a yield stress. Okay, so we studied this problem and we tried to answer 2 questions. How does this viscoplastic droplet spread, and what is the final shape? And let me start answering by the second questions and give you maybe the most important part of this, the first section of the talk, which is the scaling law. So consider viscoplastic droplet of volume V at its final shape. So this volume or this droplet has a characteristic length scale L. So if this volume was a spherical, L was the radius of that sphere, okay? It spreads, it reached this final shape, and then if you imagine this is shallow and looks like hemisphere, your volume is proportional to final height times the square of your final radius, okay? And now I can actually balance forces searching for that final radius. And final radius in particular, I should say, is important for us because that's a result somehow corresponds to the resolution of my 3D printer. Okay, so on the left, I have a capillary force. The capillary force is basically pressure, which is surface tension coefficient, times a characteristic curvature, times a characteristic area. That gives me a force due to surface tension. And I balance this with my yield stress force, given the yield stress on the base of the droplet is doing most of the resistance. So if you write this, you immediately get a scaling law. So let me walk you through this equation. So on the left of this equality is the final radius dimensionalized by the characteristic length scale. On the right, there is a prefactor omega c times to this non-dimensional number to the power -1/7. So this non-dimensional number was called capillary Bingham previously in the literature because it is the multiplication of capillary number and Bingham number. I like to call it the Plastocapillarity number because there's no velocity in it, and it's basically material properties and a length scale. Okay, so what does it do? It compares the yield stress with capillary stresses. So as yield stress value goes bigger, J becomes bigger, and therefore your radius is smaller, right? So it's not rocket science. The stiffer your material is, your droplet spreads less. So this scaling is somewhat new, but this number has been used in the literature. Wolfgang Bertola have used this review of Near also looked into the problem. And I also found this relatively old Belarusian paper that if you do the non-dimensionalization they've done slightly different, you also get the same number. Okay, so this is the balance for the time that you have pure surface tension effects. You can do the other asymptotic limit when your droplet is so large that gravity is doing all the job of spreading, right? So you can think about, again, geophysical fluids or the type of rheometry you do for sometimes for cement and concrete. And if you do so, you can balance the gravity forces with the yield stress forces, and you get another scaling. So your final radius is now balancing with, in this way, another prefactor. And now another dimensionless number shows up, which is the bone number. And bone number compares the gravitational force and the capillary forces, right? So just a quick note that what I have on the right side does not have a surface tension coefficients because there's no surface tension forces. So if you times B and J, the actual surface tension cancels off. I wrote it this way for the sake of consistency. Okay, so this is nothing new. Many work, as those cited here, have done this. And in fact, you can get this prefactor exactly because your equations are much simpler when you're in a gravitational dominant field. Okay, so we search for those, let me go back. So we search for these prefactors and also the dynamics of spreading through a theoretical framework called viscoplastic lubrication theory. I will try to explain it very quickly. So if you have a thin film that has a height h, and this height is order epsilon smaller than the horizontal length scale of this. Basically, it is shallow. You can start from Navier-Stokes, go to asymptotic limits, and for a small Reynolds number, you get this parabolic velocity field, and you do the height averaging, and you get this very or relatively famous equations. That is called evolution equation or thin film equation. I listed some review paper on top, and also a lot of people, there are many more who work on this type of equations. What you have is on the left is the time derivative of your height. And then on the right-hand side, you have the spatial derivatives, and this P is your pressure that has a first order term due to gravity. That's where the bone number shows up. And then you have higher order derivatives, which comes from the curvature and capillary effects. Okay, and there's this H cubes that is like a diffusion term in your case. You can do the same thing for viscoplastic fluids. Instead of this parabolic, nice parabolic velocity profile, you get something like this. So wherever inside your film, your yield stress, your stress is equal to yield stress. You have this yield surface, which above you have plug-like flow, right? So below this, you're shearing the fluid, but above it, you have plug-like fluid. And now if you do this derivation of lubrication theory, you arrive at this equation. So everything is pretty much the same, with the big difference that instead of that H cube term, now you have this with Y, the yield surface showing up. And you basically find the definition of the yield surface as I shown here, and I'm showing you with the mouse. So the capillary or Plastocapillarity number shows up again here. So let me tell you, before moving to the solutions, a little bit about the limits. So imagine Y goes all the way to the H, so all the way up. So I'm yielding everything, right? So meaning I have a Newtonian limit. So you see it here. If Y is equal to H, this gives me H cubed again. I have the Newtonian lubrication equation. If Y goes to 0, that's my final shape, right? Because everything is plugged up, nothing moves. And therefore, that's Y equal to 0 is my final shape. So I get back to that later. So we solve this. You can solve that equation I just showed you with your favorite numerical method. We did it with finite difference. Here is an example. This is the initial shape of the droplet that is spreading over time, and the golden profile is my final shape. So after that, droplet doesn't move anymore. So this is for these three dimensionless parameters. So to give you a sense of how the yield surface looks like for this profile in the middle, the blue one that I'm highlighting, I'm showing you the yield surface, which is shown in the dashed red line. And it also looks like this. What you don't see in this picture is what happens at the edge of the droplet, which becomes actually very important in the next type of solution I will show. So the droplet interface goes through a series of wave-like undulations, and it looks like the amplitude is exponentially decaying. So this type of undulations are very well known for Newtonian fluids. What we saw was that it also happens in viscoplastic droplets, and they're so persistent that even the final shape has those undulations, as shown here with the yellow line. Okay, so you can do this and get this final shape. But like I said before, if you're only interested, as we've mostly been, in the final shape, you can only look at this equation, right? So y goes to 0, that's my final shape. So all I need to do is to solve this differential equation. So it looks simple, but if you open it up, it's not that innocent. So it looks like this. It's relatively, it's high order, third order, and you have this switch of the sign on the right-hand side that you have to deal with. So now my problem is a boundary value problem. All I need to know is the boundary condition in the middle of the droplet and the boundary condition at the edge of the droplet, and search for the solution. So here is an example for the same numbers that I showed you. The dashed red lines is this now, let's call it asymptotic solutions, and the white line that is bang on it is my from the numerical solution of lubrication equations. No surprise, they match very well. And if I look at the edge, this is how it looks like. So this line, the undulations, smooth one, are for the interface H itself. And if I look at the second derivatives, you get these sawtooth-like shape. The reason I'm showing this picture on the right is to emphasize that this is significant to study these undulations, because that's what determines your boundary condition at the edge of the droplet. Okay, so with two notes, I go and try to wrap this theoretical part. So to do this asymptotic solutions, first you have to prove these undulations end at a finite radius, right? Because in Newtonian case, this wavelength is constant and they go forever, mathematically, of course. But here we show that they actually not only decay in length scale, but also amplitude. Therefore, they furnish a final accumulation point, and we find the boundary condition at that point. Okay, so the most important thing you can get out of these solutions is this. Okay, so I try to avoid all the algebra and give you the final results. So I can basically say that my final radius balanced like this scaling law that I showed you before, and this omega is a function of some of those, my prefactor is a function of some of those parameters, namely H infinity and bone number. And if you do a lot of those asymptotic solutions, you can put all the results in such a 3D curve, right? So what it shows is that at your H infinity, your pre-wetted film thickness goes bigger, your omega goes bigger, and as your bone number goes bigger, again, your omega increases. So all you need to know is basically, this is your scaling law. You know your bone number, you know your H infinity thickness, and you know the yield stress and the mechanical properties. You come to this table, you find your prefactor, and then you can predict what's the final radius of your droplet, which is very important for the application. Okay, so this is nice. I wrap the theoretical part, and I promise I won't talk much equations after that. Some important limits: if you have pure surface tension driven droplets and the thickness of your H infinity goes to 0, your prefactor is 1.74. So prefactor always is around 2. So we got lucky there's order 1 actually. And for the gravitational case, then your prefactor, as I said, you can find it exactly, and that's this number, 25/8 to the power of 1/5. Okay, so you now have a lookup table that is fully theoretical to find your final radius, but it was time to do experiments. Our experiments were fairly simple to do. So we have camera on the left, we have diffused light on the right. We use treated glass surfaces to avoid the slip. As you know, these viscoplastic materials also slip on the surface. What we've done, we use glasses that have positive charges on top. If you're interested on that, you can have a look at our Langmuir paper. But we inject the nozzle, fluid through the nozzle, like 3D printers work. The droplet grows and spreads, and we look at the final shape. Our material was Carbopol, the beloved simple that people in the yield stress community use. On the left, I'm showing the elastic properties of Carbopol for a given concentration. As you can see, if the stress is low, your G prime, which are the circles here, is much more bigger than your G double prime. So material is more like an viscoelastic solid, with G prime being much larger. But as you put more stress, it starts to yield, and then both G prime, G double prime fail. But your material now more looks like something like this, a Herschel-Buckley fluid. Okay, that you can get the flow curve. You can tune these properties by changing the concentration of Carbopol, and this is what we've done, and we tested many of them. So this is how a video of an experiment looks like. You inject the fluid, droplet grows, and you stop the pump, droplet relax, gets to the final shape, and the final shape looks like this. So from left to right and to the bottom, so from top left to bottom right, I'm increasing the yield stress. Sorry, I forgot to mention the exact values, but you can see as the yield stress increases, the final radius drops, right? So we measure this final radius, and it's time to compare it with our asymptotic solutions. So here is some comparison. So the lines are showing my asymptotic limits when for different bone numbers, and the symbols show the experiments also for different bone numbers. Let's go through it a little bit in more detail. So the very good thing that made me happy is basically that the scalings look pretty okay when you compare with the experiment. So if you look at the crosses, this is my smallest bone number. So my scaling of -1.7 should be valid, and it's fairly there. And it looks like that the experiments are moving towards the gravitational dominance scaling when the droplet becomes large. It looks like also systematically my asymptotic solutions are overestimating the experimental results. And there are also some some sort of behavior at large J values that doesn't follow like a scaling behavior or a simple scaling behavior. Okay, so this overestimation made us thinking that what can be the problem. First thing came to our mind was that we assume these droplets are actually shallow in our theory, but if you remember the experiments, they're not in particular shallow. Some of them actually are quite fat. So what we've done next was we tried to actually solve the full equations, right? So these are basically continuity and momentum equations. Here I'm showing you the non-dimensional one. That's you have bone number. This must be B to be consistent with my symbols. But anyway, what is important is that this deviatoric stress term is now governed by the Bingham constitutive model. So how does it look like? My strain rate should go 0 below the yield stress, and should looks like a Bingham plastic above the yield stress. But we didn't really solve for the exact yield surfaces, let's say. So we used the regularized version of Bingham model, which looks like this, basically. So in a dimensional form, I basically use a maximum viscosity. So there's another viscosity in my equations that prevent the overshoot of viscosity. So there's a large viscosity in non-dimensional form. My regularization looks like this. So there's a Ohnesorg number, you can, if you will, think about it. So materials that reach the plastic, or when the stress goes below the yield stress, my fluid flow with this Ohnesorg max or large viscosity values. We made sure that our results are quite independent of this regularization parameter, of course. Okay, we use Jerris and Basilisk as our solvers. These two magnificent numerical platforms are developed by Stephen Popinay, who is in Institut d'Alembert in Paris. And here is some results for these values. So there's no gravity in this example that I'm showing you. So everything is driven by surface tension. So this is a droplet. At the edge, this is almost times 0. You can see the deformation. I should mention the color is the log 10 of the strain rate. So basically, whenever it goes to white, I have a lot of deformation. And whenever it goes black, basically, there's not much deformation. So now with such a method, we can also look into more of the anatomy of the flow. What you will see is that, of course, you have high curvature at the contact line that drives the flow. And then at the center, something grows that looks like a static plug. There's a stagnation point there, so it's not surprising that a static plug forms there. As time goes on, there is another low deformation zone growing close to the surface, which looks like a somehow rotating, moving, co-moving plug region at the surface. What is more important for us, for our application, is at some time, like the lubrication one, everything inside the droplet, the stress falls below the yield stress, everything goes back, meaning droplet stops spreading. And that's my final radius, okay? So I can get this final radius and put it on the same curve that I showed you before and do the comparison. So it's the same comparison curve now with the blue symbols that are the simulations. So here I have simulations, asymptotic solution, experiments, all of them together. Again, the scaling seems to be fine, at least for low J numbers. But now I can see some discrepancy again. So we have our guess where the discrepancy come. We can discuss it in the end of the talk. There are multiple parameters like the exact value of surface tension of carbopol that we are not sure. When the J number goes high, meaning the yield stresses are high, your deposition history becomes very important. The way you deposit the droplet, that's why some of the discrepancies that you see here, the mess happens here, is can be because of that, and some other reasons, including the effect of elasticity, which is not in any of our models. Okay, so this sums up the spreading part that I wanted to say. Now let me quickly try to address these two other outline of the talk. How can we control this spreading? And for that, what we've done with Boris Stover and Neil Bamford during my PhD was to use this so-called thermoresponsive polymeric solutions. The polymers we used is called Pluronic F127. It's a triblock copolymer. It has PEOs on two sides and PPO in the middle. It's been studied to great details in the physical chemistry literature. I've written some here, but there are many, many more. What is super interesting about this polymer is that if you heat it up, they form micelles, and if the micelle concentration is high enough, they pack, and then they form a viscoplastic material. It's super counterintuitive if you don't know anything about them. Typically, if you have a polymeric solution, you heat it up, the viscosity goes down, but this one is a magical one. You heat it up, it suddenly turns to viscoplastic, yield-stress flow. We've done some comprehensive rheology of such materials. I don't go to the details, but here is a summary. Y-axis is the temperature, x-axis is the concentration of polymer. If they're both low, you have a Newtonian fluid, and there is a sharp jump to the yield stress materials that is over this line. And what we also found out, if you go to very high temperature, something weird happen. You get negative viscosities in your flow curve. We couldn't repeat those experiments. More recently, the group of John De Bruyn, Hopkins and De Bruyn, this very pretty nice Journal of Rheology paper, look at the same fluid, rheology of same fluid, and found out that this behavior is most likely associated with the long relaxation time of the polymer. Have a look at these two papers if you're interested in the rheology of this. Okay, so what we've done in our setup, we did pretty much the same thing, camera and the light. We now inject the fluid, but we also have a heater to heat this fluid from bottom to basically turn it to viscoplastic to see if we can control the spreading. We also did something else, actually. We, on top of this spreading droplet, we put a device, an optical, we use an optical technique called optical coherence tomography. For the experimentalist in the audience, this is basically an interferometer using white light, which basically do the interference of all the wavelength of the white light, and through that gets information in depth. Okay, what we did is we actually did a little bit of modification, and we tried to do some sort of microrheology. So we added microparticles to our thermoresponsive polymers like this. So the measurement voxel of this experimental technique is around 10 to the power 3 micrometer cube. And we put smaller particles inside it. So what these smaller particles do, they do when they do Brownian motion, they do local light interference, which results to this so-called speckle patterns. So if they are in gel, they don't do, they're trapped or caged in the polymeric matrix. They don't do Brownian motion. But if they are in a Newtonian phase, they do the Brownian motion. So that was the idea. And this is the type of dynamical signals that you get. So on the left is low temperature. So my fluid is Newtonian. And on the right, you see the high temperature viscoplastic ones. You don't see the particles, but you see their macroscopic manifestation in this dynamic speckle pattern. Okay, so here is one example. So this is a droplet heating from below. We did cross correlation to find out where the fluid turns to gel first, so we become viscoplastic first. It surprised us in the very beginning that, as you also saw, the gelification starts on the interface of the droplet first, and then comes from the heated surface. It puzzled us for a while, but what we found out is that such behavior is because of evaporation. So a little bit of heating, you heat the air to water escape, polymer concentration goes up, meaning gel temperature goes down, and your polymer turns to gel. So with this technique, we actually went way beyond what we really wanted to do in these experiments. We found out we have an in situ measurements of what really happens in a droplet that is changing its phase because of temperature. So does it happen for the spreading droplet? Yes. So ignore this curvature you see on the bottom is an artifact of the method. So what I showed you was a thermoresponsive droplet spreading on a heated surface. Droplet is in full Newtonian phase. This stops at some point, and then we can see the formation of gel. So through this method, so here is a snapshot of the same video I showed you. So droplet spreads, it stops, no sign of gel formation, but then after a while we see that the gel starts to form inside the droplet. Which actually these experiments made us answering one classic questions in solidifying spreading droplets, which I come to. So two main things we found out. First, this is an effective technique to control the spreading of droplet on the surface. So what I'm showing here is the final radius and y-axis as a function of heating rate. You heat the surface faster, you get a smaller droplet. And the cool thing about these polymers are that you can actually do the cooling, so you can reverse the process, and then they become gel, like a Newtonian fluid again, and you can wash them off fully. Okay, so you can use it as a like a smarter way of printing and removing and printing and removing, if you want to use it in 3D. And we also, as I said, there was this long-standing questions of what stops a spreading droplet that is solidifying on the surface too. There were two dominant theory in the literature. One of Sonin in MIT, that he assumed that air is insulating, fully insulating. Therefore, the fusion front looks like this. There is a counter. There was a counter theory of a group of Piruskov-Vapuri in UCLA that say no, actually because of air you get a solidification front looks like this, and that will stop the droplet. So here, some of the first time we actually presented direct experimental observations of what happens. So what we saw is that what kind of stops the droplet in this regime that we are talking about is this contact line, microscale contact line solidification. That's enough to arrest the droplet while it spreads. Same thing works for impacting droplet. As long as your Reynolds number is not huge, you can control the droplet final radius with just changing the temperature of the surface. X-axis here is a non-dimensional surface temperature. Y-axis is my my Reynolds number, and here I'm showing you the final radius. You can control your final radius either by Reynolds number or by just changing the temperature of the surface while using such polymer solution. Okay, so I answered the second questions to some extent too. And last thing I want to say is what we tried to do in the past 2-3 years at Physics of Fluids group at University of Twente. The big motivation was that whatever I showed you so far was with nozzle-based 3D printers. If you have a 3D printer at home or at work, I have a few here. You know the nozzles are they could be pain in the neck because they clog all the time. So what we thought that can we actually have a system of printing that has no nozzle, because clogging, we want to avoid clogging and the cost associated with that, and we want to go actually much faster too, if possible. So we start looking at the literature, and we found out there are works already on that, and we start focusing on this laser-induced forward transfer. If you're, as I said, people have looked into this, in particular in optical engineering and printing engineering. There's a very nice review paper by Sarah and Picker. You can have a look at that for the review of advancement technology there. So what is Lyft, or laser-induced forward transfer? In theory, it's very simple. You get a laser pulse, nanoseconds or picoseconds. You guide that laser pulse to hit your ink, your viscoplastic material. And what we also did, that we actually added units of optical systems to control the power of the laser. We have high-speed imaging now to look at what happened after we shoot the laser. And we also had another optical unit to control where we focus the laser in this thin film of viscoplastic fluids. This is what happens. This is my carbopool solution now. This is glass. I shoot the laser and I form this jet. So the idea is, if I could control this jet, I can actually use, like, you know, what you do in inkjet printing or your extrusion printing, and print with the droplet. one or two slides on how this system actually works. We, in fact, are printing with bubbles. When you shoot a laser, when you focus a laser in a thin film of a liquid, what happens is this. This is videos in 5 million frames per second. So this is a very, very fast process. So what happened, and you probably missed, is this very beginning that I tried to stop the video. So this bright spot is the plasma that you form. So you break the liquid thermally and optically. You form bubble. It's a gas bubble that grows, and this bubble, since from now on, control the dynamic of the surface. Plasma forms, bubble grows, push the fluid on top, bubble stops to collapse because of the pressure around it. And this whole phenomenon, we explain it in detail in some of our papers, forms this jet on the surface. Okay, we did a little bit of theory. I didn't go to the details, but what we did, we actually found a characteristic velocity of such a process by balancing the laser energy with the other parameter, initial parameters in our problem. You get this characteristic velocity that has a lot of terms in it, but with that, you can now define your non-dimensional numbers that has yield stress and other rheological parameters too. Okay, so we controlled now this jet. So this is what happens. Everything is the same in these two videos I'm going to show you, except the yield stress, except the rheology. So this is low yield stress. Everything is splashing around. You don't want to print with such a jet because, you know, there's a lot of residue. But if you tune your rheology with a little bit of carbophyll, for instance, you can get this very nice jet. So this is perfect. If you put a surface here, this jet gonna touch the surface, and it comes down and leaves a tiny spot of my ink on it. We found out what is an optimal printing regime or region. So based on Reynolds number and Weber number, and that is this is fully empirical, some in this triangle confined from Reynolds 200 and these two owners of number. Okay, so wherever you know your material properties and laser optic properties, all you need is to find Reynolds and Weber, come here, find your sweet spot of printing with laser-induced forward transfer. With this method, we actually could print quite a lot of complicated structures. I wasn't sure because of copyright issues if I could show those pictures, so unfortunately I couldn't. But if you're interested, shoot me an email or message me. I will show it to you in person. Okay, before I finish, I want to address the elephant in the room, which is elasticity. There's always questions. What about elasticity? These are I talk about yield stress and viscosity, but I didn't say anything about elasticity whatsoever. If I want to quickly address this, so whatever I showed you, you can, of course, add elasticity to your constitutive model and see if it is important or not. So these equations that I'm showing here is a relatively simplified version of what Saramito's model, the one in here in JNNFM paper of 2007 has. I got this equation actually directly from the beautiful paper of Liu and Forte. What it says is that below the yield stress, or here critical yield strain, your material looks like an elastic Hookean solid, and above it you have this viscoelastic response. So here this is elastic solid, and then you have this creep term that gives you additional time, which is this lambda relaxation time that somehow is approximately like this. Okay, so if you look at your material like this and within the context of what I showed you in this talk, elasticity becomes important in at some point. For instance, in the when the droplet wants to stops, you can look at the non-dimensional number of like Deborah number, and that suggests that your elasticity might do something. We haven't looked at it. It might be important. For the case of Lyft, I don't think elasticity is actually important in the time that I've shown you at the very beginning. Later, of course, when the droplets are formed or in the process of extension, and when the droplets is relaxing on the surface, elasticity is important. So I think it is important to look into elasticity at some point too. A very extreme limit is that I only have elasticity fighting with capillarity flow, and there is a whole field of elastocapillarity. If you're interested in that, these two annual review papers are actually very, very nice. Okay, so I try to conclude. I gave you a little bit of information about viscoplastic spreading. This scaling law is so easy to look at. This omega, you shouldn't be worried about it. We did asymptotic solutions to find it for you, is around 2. We showed that you can use term responsive spreading as an effective way to control your final shape. And you can do with this method with optical coherence tomography, you can actually observe phase change in situ in your fluid. I also talk a little bit about laser-induced forward transfer of viscoplastic materials. That is very, very promising, actually. Have a look at the future. Of course, I still believe with the so-called simple yield stress fluids, theoretically, numerically, and experimentally, there is a lot of room, like the interaction with the solid surface, more application in the printing. But of course, looking at elasticity can be very interesting, and also like phenomenal, like the extension of these fluids. I want to end by thanking all the people that I worked during the past few years. I've been very lucky to work with all of them. Neil Bamforth, Boris Stover are my PhD advisors, and that most of the works I present on droplet spreading, all of them actually are was with them. I learned tremendously from them. Detlef Loza was my first postdoc advisor, who all the Lyft work that I showed you was with him. Jaakko Snoja in the same group was my mentor. The Newtonian spreading was with Jaakko and Carola. Carola, Wetzel, Dave, and Martin are excellent bachelor, master, PhD student who worked with me on this project. Thank everyone, all the supporters, and of course, thank you for listening. I would love to take any questions.
Thanks, Mazi. That was a lovely talk. The first question is going to come from Cecile, and let me just see if Cecile, you there?
Yeah, can you hear me?
Yeah, loud and clear.
Perfect. Hi, very super interesting talk. Thank you. So I was wondering, I think at the very beginning of your talk, when you said you were going to present a simplified spreading model, you did not take into account any wetting effect. So I was wondering what happens if it's not a perfectly wetting liquid or complex liquid.
Excellent questions. Well, the short answer is I fully don't know yet. So we look at the asymptotic solutions that I showed you. You can do the same thing if you actually did it with a constant contact angle. So that change your boundary condition at the edge of the droplet. And but what I'm concerned is more in the reality, in the experimental part, because the interaction of polymeric solution at the contact line is not yet very clear to me. This is something we are looking at it right now. It becomes relatively complicated in a small scales, especially having experimental access to that scale is hard. But it's a work in progress. I can't say much. I mean, theoretically, you can do the same thing. You can get your prefactor for as a function of contact angle, let's say, for partial wetting. Experimentally, we haven't done the experiments in full detail to compare to see how good they are.
Okay, thank you.
Thank you, Cecile.
Thanks, Cecile. Next question is going to come from Hamid. Hamid, are you there?
Hi.
Hi.
Hi, Rob. Hi, Ian. Thank you very much. Thank you, Mazi, for the very nice and great talk. I really enjoyed. One question that I think it's raised on my mind. What is the characteristic time scale that's it's first for the formation of the viscoplastic that you mentioned in your talk?
So in terms of the like a droplet spreading experiment.
Exactly, yes.
Several seconds. So those experiments that I showed are several seconds. I mean, in general, the time scales is a function of, or the spreading time scale is a function of your yield stress, surface tension, this plastocapillary number J that I showed. So if it's basically, you can think about if it's 0, it's like Newtonian, so it's gonna be longer spreading. If you're looking for the dynamic, maybe your question is more about
yeah, exactly. I'm going to go to the microstructural dynamics of the system. And also at the end, I'm trying to connect with some word like elasticity that you also commented on that.
Sure. I mean, but I can show you. I mean, maybe if you see this.
Yes. Yes.
So here is. I mean, I didn't talk about dynamics at all, but so the picture on the right, for instance, shows my radius as a function of time. So if your plastocapillary number is 0, you get to this very famous Tanner law for fully wetting, which is your radius very weakly spreads over time with the power 1/10.
Yes.
And as you add plasticity, so at some point you start to deviate from that and approach the final radius. So you can get and then the question is, what is the final or stoppage time?
Yes.
Which I can address that with it's very hard to address with, for instance, the numerical method that I explained, because we use regularization.
I see.
In the experiments, you can get a sense that, I mean, in let's say, it ranges in the seconds if you're looking for a number when you use Coherence solutions, for instance.
I see.
Just to follow up, Mazi. I mean, what's your opinion? Is there a finite stopping time?
I think there is a finite stopping time. Yeah, there is definitely a final stoppage time. And I guess with some of these methods like minimization of energy and those things, maybe one can actually find them. I'm really no expert in those type of calculations. I know you are in. So I think it is possible to get the final stoppage time. We have an estimation of it, but yeah.
Yeah, I mean, there was that paper by Hogg years ago that, showed things were just asymptotic, but in those analyses you already do the thin film stuff, don't you? So you're almost assuming that they're flowing before you do all of the estimation. So
yeah,
you kind of feel there should be, because of the yield stress, that should just run out of steam and stop. But
yeah, I also think so. I really don't know the mathematical details, so I can't really comment. But I mean, reality, if I do the experiment, there is a final stoppage time. Yeah. So things stop. And that's when you go to elastic solid or viscoelastic solid regime.
Okay, thanks, Hamid. I hope that answers the question. The next question is going to come from, it's actually Bud Homsey, but for some reason, Bud was showing us Bushra Iqbal. Bud, are you there?
Yes, I am here.
Hi.
Hi. Well, this is the kind of talk where you listen and you have a question, and you listen some more, you get another question, and then all kinds of questions occur to me. So I'll try to limit mine to 2. The first is, of course, having to do with lubrication theory. It seems that one of the real problems in 3D printing is coating over topography. That is, multiple drops coming and forming objects and spreading over topographical features. And so it occurs to me that you're well positioned to look at some of those problems. Many years ago, Stillwagon and Larson published a key paper about coating over sharp edges. And most remarkably, it turns out lubrication theory can do a pretty good job, even though there's a singularity in the geometry. So I guess it's more of a comment than a question, but have you thought about that as sort of an interesting next step to take?
Absolutely, but 2 things I'm doing in the lab right now are to print or deposit droplet on top of another droplet and depositing on a curved surfaces or rough surfaces. These two are exactly the very steps that I'm taking now, because they're, as you said, crucial. I mean, especially droplet on droplet, because, or multi-layer, what they call multi-layer printing.
Yeah,
Uh,
yeah. Well,
especially
coating over rough surfaces, you can easily anticipate that the thing is gonna, the yield surface is gonna plug up the divots, and
Yeah.
so you'll have a big change in the final radius as more material gets frozen up in the divots. If I may, Rob, well, you know, I'm famous for getting the microphone and not giving it up.
No problem, Bushra.
Could you show you had a plot toward the end of Reynolds versus Weber for
Yes.
the jet study? Could you show that again?
Sure.
It was one of the,
Yes.
yeah, this one. Okay, so what strikes me here is on log coordinates by eye, anyway, my eye, I've had enough coffee to do this. It looks like Reynolds is proportional to Weber, which means that Reynolds over Weber is 1 over the capillary number.
Exactly.
And so it seems to me that maybe density doesn't have anything to do with this set of dynamics. And if you renormalize the data Reynolds over Weber, you'd get unique values for each of the experimental studies, the fragmented jet, the jet. In other words, you get a flow regime map that's independent of density and just has to do with what is the capillary number. So you could get to a simpler picture of these data. Again, it's more of a comment than a question.
No, that's very correct. I mean, I'm glad you mentioned, so I can elaborate a little bit. So you see these two white dashed lines that somehow envelop my experimental data. Those two are actually two constant capillary numbers. And this happens because of my dimensional space parameter. So the density of these fluids being carbopol solution is almost the same for all of them. And each of these lines somehow, if you could see, I mean, it's hard to see, basically each of my set of experiments that I do with a given fluid gives me more or less in a straight line in this phase space. The reason we ended up using Reynolds-Weber with Ohnesorg number on top is to be consistent with the literature of inkjet printing that do exactly the same thing. So they use pretty much the same numbers, and they used some cross Ohnesorg numbers to define their favorite spots for printing. So that's pretty much the only reason we use this. It's quite empirical, the whole thing.
Thank you very much.
Thank you both. Great to see you.
Thanks, Bud. So the next question is going to come from Antoine Deblay. It's a bit of a follow-up question from Cecile's, but we'll get him to ask it. Antoine, you there?
Yes. Can you hear me?
Yes.
Yeah. Thanks, Mazi. It was a really nice talk. Well, I had a question. Maybe indeed it was related to Cecile's question, and I think someone raised it in the chat. Maybe first, how would you measure or how do you measure the surface tension in your carbopol solution? And how would you vary it actually, if you want to vary it?
Excellent question. I'm also very happy that you asked this, so I can raise that concern somehow. I wish I had a slide of a separated slide for that. So there are works on measuring surface tension of carbopol in the literature. There is one work from Marseille. I forgot the first author name. I forgot her name. There is some work from the group of Cousseau, and there's a few more. There is one actually from the group of Daniel Bone on the extension of carbopol that estimate. So the value reported varies. It's close to water, less than that, so 0.06 or something. We didn't measure it. We used an average value of reported values. That can be one of the reasons our results are not matching the theory. I think the group in Marseille have shown elasticity can be important when you measure surface tension. I do not have any golden idea how to measure it properly. I think the extension and looking at the jet that is, or this the pinch of the extending carbopole can be a good way, as happened in that paper PRL with group of Daniel Bone. But I think it's needed. Okay, let me put it that way. I think it's really needed that we make a good method of measuring surface tension of yield stress materials. None of the common methods work fine when your fluid has a yield stress. This has been also told by others, but yeah, I think it's something to look into.
And then, thanks, Mazi. And then may I just ask the second question then related to that? I think you showed in a sequence of pictures that when the droplet is spreading over the surface, I noticed that maybe the contact angle, or namely the advancing contact angle, is changing in time. I mean, is it due to some, I don't know, defect on the surface, or as you say, the or whatever?
I'm not sure if I understood correctly what you're addressing, but something like this, you mean?
Yeah, at a certain point you showed like maybe a close-up of the advancing contact line, or I don't know. I noticed that the contact angle is changing much, and I was wondering about yeah, this surface tension question actually, if it was connected or not.
Yeah, I mean, I think it is. It is basically surface tension and yield stress. So let me elaborate a bit. The actual contact angle is 0 here, right? Because there's a pre-wetted film. The macroscopic or the apparent contact angle varies.
Yeah, that's what I mean. Yeah.
Not only for advancing one, but also for the final shape, as I'm showing here. And I was actually also suggested by some of the people previously that maybe we actually can use these experiments if we really trust our theory to measure the surface tension.
Yeah.
And could be, but we need to first show that the theory works perfectly. We are talking about really small values and a small variation of the surface tension. So yeah, could be potentially, but yeah, I mean, if I want to basically put my money on one method of measuring surface tension, I will at least start with the stretching experiment and the pinch of experiments.
Okay. Okay. Thank you very much.
Thanks, Antoine.
What about mixing the carbopole with different solutions, rather than just water? We've certainly mixed with sugar solutions and glycerin solutions, and we haven't really thought about surface tension, but there must be other options there, I would think.
Indeed, I mean, Antoine asked, I forgot to actually mention, if you add glycerin, you keep the yield stress the same, you change the viscosity. It's perfect way of doing that. But if you add surfactants, I assume you can also change the surface tension. Actually, I haven't done it because carbopole is not a good surfactant. So if I think if you add, I don't know, some sort of good surfactant in water, you can actually tune the surface tension. I agree. Yes.
Yeah. Okay. Next question's going to come from KVS. KVS, you there?
Okay. Hi, Rob. Can you hear me?
Yes. Yeah.
Hi, Mazi. I have a question related to the literature in this area. I'm new to this area. So as you may know that there are several works related to a Newtonian fluid drop in a Newtonian fluid. Maybe starting from the seminal works by J.A. Taylor, where he looked at the translation of a drop or the deformation of a drop in a shear flow or a quadratic flow. I would like to know what is the status of understanding of these kind of problems with a viscoplastic fluids. Maybe the drop is a viscoplastic fluid suspended in a Newtonian fluid or something. So is this an open question or?
There are very nice questions. There are not much work on it. We are doing bubbles in shear flow simple shear now with simple Bingham model. I know the group of Uti, help me with the last name, in Sweden in KTH. Yes, she's also, her group is also looking at those problems. I don't know the status of that. If she's in the audience, maybe she can come. But not, I mean, in short, not much work on that as far as I know. I don't think there's much work on, for the particles, of course, there are some really nice work, the work of Sarah Hormozi, who also presented in this series, and a lot of other people. But for when the self-extension becomes important, not much work is out there.
Okay. And to continue, I have one more question. So regarding the experiments in this area, are there some studies like coherence effect with the yield stress fluid or dispersion of particles, something like that, or it is also not explored?
Well, there is a very large body of work on polymeric droplet evaporation, which is way more complicated than just the covering effects, because the polymer itself. So I showed you some hints of it with the term responsive one. So your polymer also form solid-like structures when it evaporates. Right, so you're, if you add particles, you complicated things. I guess there are a lot of problems already open for polymeric droplet solutions, evaporation of polymeric droplet solutions. But of course, you can also add particles and try to avoid coherent phenomena with polymers. I'm not very. I know the coherent literature to some extent, but I'm not that updated. I think there are works with control with polymers, but have a look. I'm not sure.
Sure. Yeah, thanks a lot.
Thanks, KBS.
Go back to your first question, KBS. There was also quite a lot of work done by Avenir and his collaborators over the years. And so they do things like a yield stress droplet, within a Newtonian fluid, and then they use, sort of semi-analytical type of methods, and things like boundary element methods to do the Newtonian part, and then I think they resolve the, the viscoplastic part. I think they have to do it numerically, but there probably is some scope there to do some more analytical things, I would think.
Yeah, indeed. I mean, the group of Avenir have done a lot of work on droplets of viscoplastic fluids, also bubbles a little bit, and also a group of John Somopoulos, but they're all numerics.
Okay,
fantastic question. Thanks, KBS. So, Mazi, do you want to keep going? We're down to a few questions. It would be Cecile again next, or?
Oh, sure. Yeah, absolutely. I'm free.
Okay, well, let's go to Cecile again. Cecile, sorry, I didn't give you any warning. Are you ready to ask your next question?
It's fine. I'm here.
Yeah, great.
I was wondering if you also investigated the Leidenfrost effect with your magical thermal responsive complex liquid.
No, we didn't. We didn't go that high temperature for the to see the Leidenfrost. So you need to evaporate or boil something, or at least to get a critical Leidenfrost temperature. We never went that high. I don't know what happens.
Okay, I was gonna say, what do you think would happen? Okay.
Yeah, I mean, I'm trying to. It's now science fiction, but I think if your droplet goes to Leidenfrost state, so it somehow levitates on this vapor, but temperature is high, so you're probably gonna turn to some sort of gel. But that is so high that you get to this weird rheology regime that I showed you. So you might actually start degrading your polymer. I really don't know what happens. So maybe it's a way, if it evaporates, obviously evaporates, and maybe you start making polymer capsules. Yeah. I mean,
that would be interesting.
Just imagine.
Okay, thank you again.
Thanks, Cecile. Next question is going to come from Ricardo. Ricardo, are you there?
Yes.
Hi, nice
Hi,
to meet you.
I had a question about the gelling droplet.
Mhm.
I guess influenced by Detlef. Is there any evaporating cooling in the droplet happening at the same time, or do you think you can ignore that? I mean, you see that the gelling it happens from the surface, right? And you say that the answer was evaporation, and then that just made me wonder.
So in the same paper, we have an appendix trying to provide some simple theoretical or calculation of what really happens in terms of evaporation, time scale, and those things. So the answer is no. We didn't look into the evaporation cooling.
Okay.
I also don't know how important it is. What is obvious from the experiment is that evaporation at the surface leads to this skin formation in the droplet.
Yeah. Okay.
It's a nice detailed question, Ricardo. I have to think about it. I don't know if it is important or not. But
yeah, because from one side, I think evaporation, you say it causes to increase the concentration, but on the other side will go to try and avoid this temperature effect, right? So yeah. Maybe they are just detailed.
Okay. Yeah, I mean, obviously evaporation is dominating in the sense that it tends to gel. I mean, you could do the experiment without hitting the surface and you see exactly the same thing without, of course, this part that comes from the conduction, you see? So without this, if you let the droplet evaporate, they start this from the skin and then the rest happens. So it doesn't, at least all I can tell you is that the surface cooling because of evaporation never dominates such that you don't get the skin.
Yeah, okay.
But how much is it? I actually don't know. I didn't never try to calculate that. But very nice detailed one.
Yeah, thank you.
Thanks, Ricardo. So we've got a couple more questions. Next one's from SW. SW, let's see if SW would like to ask his question.
Hi, can you hear me?
Hi.
This is very nice talk. It's very interesting. I'm wondering, can you comment on the fusion of the droplet next to each other, or something like a well line happened during the 3D printing?
Yeah. So the model that we let me just quickly go through my slide to see if I have a backup slide on that. I don't. The theory that I showed, the viscoplastic lubrication theory, is very, very easy to be modified to study that. I actually have done that already. I mean, all you need is to change the initial condition. You can also do some nice mathematical, theoretical investigation of what happens when two droplets start to merge. Experimentally, we need to do more experiments to validate. My guess is that the same sort of similarity that we saw in the spreading gonna happens there. Obviously essential, it goes back to the question that both Hamzi also asked before, that it's essential for 3D printing to look into how droplet are spreading on top of each other or next to each other. And that's a step that we are taking now. But I can tell you theoretically and numerically, what I showed you is very easy to be extended to that problem. And experimentally, you need a little bit of modification in your experimental setting.
Thank you.
Thanks. So we'll have the final question from Hugo Perrin. Hugo, are you there? Hugo, do you want to ask your question? Silence from Hugo.
He's muted, I can see.
Yeah, I've invited him to ask his question, but maybe he doesn't want to. It was just a question about the technique I think you're showing on that slide with the particles. I guess his question is, when you have the particles and they're in the gel, it could still be unyielded, but in a plug, so it could still be moving. I guess I think is his question. A very nice technique about the speckle. One question: the plug flow would also decorrelate the speckle. Is it not necessarily a yielded area?
Well, the plug flow is when you turn to gel. So what I showed you, so that's if you have plug, you basically have gel, if I'm right.
I think he means that, you know, it could also be, you know, moving. It could be it could be not deforming, but all moving at the same velocity. Yeah.
Yeah. Okay.
Yeah.
I guess. Yeah. I mean, I can read the question in a way the other way around. So I have a Newtonian fluid that is moving, and maybe. I mean, we don't have much strong convective flow in any of these experiments that I showed you. If you have, for instance, the pipe flow of yielded stress materials with this thermoresponsive one, I guess that become more challenging because you have to think about the convective flow, but which there are ways, because this device gives you way more than what I just showed you. You can get a lot of phase information and try to correct for that.
So Hugo just apologized and said his mic isn't working, but I think that kind of answers the question. So that's, I think we've gone through a whole, I think there's at least 12 questions there. So thank you very much, Mazi. That was a beautiful talk. This is where Ian comes in with a couple of really challenging technical questions now. This is his style. So Ian, have you got any questions?
Well, yeah, well, I have a few, but I think I've asked you some of them before, so I won't ask you those again. One that's always interesting with these final shape things, you know, where you have your steady equation. So you get, you get a shape. So when you do the type of geometries you're doing, they just go and sort of fill out that shape. But I'm just wondering, you should, so that final shape is really then just, a property of your Bingham number, your J number, or, some combination, and the volume, isn't it? Yeah, it's basically those three things. So, when you do a transient problem, do you always get to that shape, or can you find, can you find initial conditions where you can somehow sort of stop before you get there? I mean, it sort of implies that you keep filling out the shape, doesn't it? And
it's a great point, and you're absolutely correct. If your yield, I'm not talking about the theory. I'm talking about the general problem now first. If you have a droplet that has a yield stress and you're depositing it on a surface, it heavily depends, especially when the yield stress is lower, it heavily depends on the history of the way you deposit, because it depends how it's like a sculpturing, right? It depends how you form your sculpture. In the theory, the assumption is that everywhere inside the droplet is yielded in the beginning, and that results to the same final shape in the end. So with that assumption, the final shape is the same in the end, because this differential equation gives you that shape. So you have boundary conditions that you need to satisfy, and there's one solution to it. But it is not what happens in reality, and that is one of the reasons that I try to highlight in this curve when I compare everything here. So if you look at this data here, they're a little bit messy. These are data when yield stress of carbopole is actually large. So when I deposit the droplet with my nozzle, I don't necessarily yield everywhere inside the droplet, Right. There are some parts of the droplet that never yields, and that gives me different shape and obviously different radius. So that's a shortcoming of the theory, indeed. And yeah, I mean, I'm not sure how. I mean, you can do simulations like this, and then you're not limited to anything, right? I mean, you can deposit any shape anywhere.
Yeah, I guess for these ones, most of the ones that we sort of see people do exactly this. They put it in the middle. Mm-hmm. But I suppose if you put it in an annulus or something like that, you would still have the same boundary conditions at the center. It would still be symmetry conditions. but you know, it would have to spread in as well as out, wouldn't it? And I wonder if you would get to that shape.
I'm not sure if I understood the analysis geometry, what you exactly mean by it.
Well,
A gap in the middle.
Yeah. Yeah, you could pick any.
Extrude through an annulus, so there's a solid bit in the center, so there's a gap. Then when you extrude, as a kind of curtain, so it can also.
Yeah, so you don't have to have h equals 0 in the center, but you could have small h in the center, and then you know, a shape going up and down, just as an initial condition.
Yeah.
And
I see what you're saying.
yes.
I think if your initial condition is such that you yield everything, I didn't go so extreme with my initial condition, but I did change it to see if my final shape is the same. And as long as I am yielding everything, it is the same, the final shape.
Yeah.
But
No.
but if you, I'm sure in reality it does change the final shape. But theoretically, I mean, the geometry you mentioned could be interesting to have a look and make sure. But I think as long as the boundary conditions are the same, equation is the same, you get the same results, which is the same final shape.
It was always, it seemed amazing to me that the lubrication theory did so well, because when you actually showed the experiments, it looked so far from where you would imagine the lubrication theory would hold. You know, they were aspect ratio 1, weren't they? You know, kind of the height to the radius.
That's the same with the lubrication theory in Newtonian fluids, right? I mean, Bott mentioned one example in this talk, but in general, I guess lubrication theory works fine, and no one knows why.
Yeah.
It's practical asymptotics, epsilon equals 0.1.
But it's not even that, like, it's like epsilon equals 1, isn't it? I don't know. Yeah. I think we should end there, because that has been fantastic. What we normally do now, Mazi, is a round of applause from around the world. So from the UK and from Canada. It's a fantastic talk. I really enjoyed it. Thank you.
Thanks so much. Thanks for having me. I appreciate it. Thanks everyone for joining.
And you could tell by the questions that people were really interested as well. And there's lots of chat back and forth.